This is one of the key points in today's talk, is that repulsive gravity is a feature of Einstein's theory, even if he didn't know it. Okay, and that sounds like the world's biggest oxymoron, because the word gravity, I mean, it's, it means heavy, it means, being pulled to the earth, so what is repulsive gravity? So gravity not only can pull things together, that's how we think of it, it's attractive, that's its defining feature, but really weird stuff, we'll get to the really weird stuff, can have repulsive gravity, and that's called dark energy. And I'll tell you why I called it dark energy in a second. But let's talk about that just a little bit. And actually, Alan Guth, I know, touched upon this morning. And that is an amazing feature of general relativity, is that what causes gravity, or what the word we use is sources gravity, is not just matter or energy, but it also depends on what the stuff is made of. In fact, let me just go to this slide and remind you about Newtonian gravity. So remember when you learned about Newtonian gravity, the force of gravity that an object exerts only depends upon its mass. And you all know that. And you know it so well that you probably don't think it's remarkable. I mean, probably you didn't have a teacher who said, that is the most amazing thing. Imagine, it doesn't matter if it's a block of lead or a ball of gas, the force, the gravitational force it exerts only depends upon its mass. I mean, that's really remarkable. And that's true in Newton's theory. In Einstein's theory, if you think about gravity instead of being a bending of space as a push or a pull, the strength of gravity also depends upon the composition. So that's built into his theory. And Alan, I'll write this two different ways. So what I've written here is that the strength depends upon the amount of mass or energy plus 3 times the pressure. So the surrogate for what it's made out of is the pressure. And so what that means, for example, so what's something that has a lot of pressure? A hot ball of gas, like the sun. So if you take an object with the mass of the sun that's cold, and you take the sun, which is hot, and they both have the same mass, the gravitational field of the sun will be slightly stronger. Now, it's a very, very tiny effect for ordinary stuff. It would only be larger by about a part in a million. So let's go back. So this is the formula that Alan showed you. Is what sources gravity is rho, mass or energy density, plus 3 times the pressure. Now, mass or energy density, I don't want to get into a big discussion of that. We don't like the idea that it would be negative. Okay? But pressure, what would negative pressure mean? Negative pressure, so pressure is an outward push. Negative pressure is how we describe something that's elastic, like a rubber band or a rubber sheet. So having negative pressure is no big deal. I mean, it just means that something is elastic. So if you look at this formula, rho plus 3p, so if you had something whose pressure is negative and more negative than 1/3 of its energy density, then its gravity would be repulsive. Now, Alan, I did a cheat here that Alan didn't do this morning, is there's some speed of light squared here that I didn't put in, that Alan put in this morning. So the sun, the pressure of the sun compared to its energy density, the pressure is 1,000,000 times smaller. If you look at a rubber band, I don't even know how much smaller the P is, but it's billions. So something whose pressure is comparable to its energy density is really weird. I mean, is unusual. I'll give you an example. The simplest example is the cosmological constant or vacuum energy, and so I'll do that. And for that, P is equal to minus rho, and if P is equal to minus rho, then rho plus 3p is equal to minus 2 rho. So that's really, really repulsive. So right in Einstein's theory is the prediction that gravity can be repulsive. So the definition of dark energy is stuff that's very, very elastic, so elastic that its pressure, so its gravity is repulsive. And let's see, we did that slide. So now you're caught up with us. So accelerated expansion is caused by the repulsive gravity of dark energy. Any questions? Do you all understand that? Well, of course you don't. We don't understand it. So what is this stuff? So, here's the naming. Let's take a brain break. So how did this dark energy name come about? So, in May 1998, I convened a focus group. And I said, we have this new thing in science, and we don't want it to be scary, and let me tell you about it, and we're thinking about calling it funny energy. And they said, that's really great. That's really great, because that's not off-putting, and it's not scary, and so there's the slide. This slide actually appeared in the New York Times, funny energy. And then I said, but it's going to take a couple $2 billion to understand it. And they said, oh, you need a more serious name than that. So first example of what dark energy could be. And this is the Zen part of the talk. So it's the energy of nothing. So what is nothing? Nothing is something. Okay, are you with me on this one here? Nothing is something. So according to quantum mechanics, nothing is filled with particles living on borrowed energy and borrowed time. Kind of like New Yorkers. At least that's what I heard. And so these are the virtual particles of the quantum vacuum. We know they're there because Willis Lamb did experiments at Columbia University in 1948 and detected their effect on hydrogen atoms and got the 1955 Nobel Prize. And I bet you won't ask for proof of this. If the energy associated with these virtual particles, if there is an energy associated with these virtual particles, I can prove that the pressure is exactly equal to minus the energy density. Okay, so it has repulsive gravity. So we've reduced this to calculating how much nothing weighs. So here we've put the theorists on the spot. The theorists have to tell you how much nothing weighs. And so we've calculated it, and we've almost got the right answer. Well, we're off by 10 to the 55. Good enough for government work. Actually, this is where we really, you see us turn into a puddle of goo. Because the way I like to defend us is to say that actually the answer we get is infinity, and infinity is not a number, and therefore our answer is not wrong, because we haven't gotten an answer. Did you fall for that one? So it's better not to get an answer than to get a wrong answer. But you got the idea that when we try to calculate, so it's perfect. It has repulsive gravity. We just can't calculate how much there is. And so this is in science. Oh, yeah, I already said that. I already told you about them. Hang on. I wanted to show this again. So two things I want to say here. Number one, this vacuum energy, this thing we call vacuum energy, I'll show you this picture, is mathematically equivalent to what Einstein called the cosmological constant. Except now, he didn't understand why he put it in his equations. He put it in his equations to get a universe that didn't expand. This energy of the vacuum, in principle, is there because the vacuum is filled with these virtual particles. Okay. Well, let's just see. Let's just suppose we got the right answer. Does everything hang together? And that's what this picture shows. So this axis here is omega matter, how much matter there is. This is how much vacuum energy or lambda there is. These are all the measurements. And all you really need to look at is the bullseye there at the middle. This works really good. And as my wife would say, you meant to say well. Yeah, it works well, too. And so that's the number you would get. You would get about 73%. And so why don't I end right here and say, it's just the energy of the vacuum. One of these days you'll get it. And so let's see. So it's lambda. We have testimony that you walk like a duck and you quack like a duck. Tell the court, are you a duck? So that's the way we think about it. So why aren't we satisfied? Well, we don't have a good theoretical understanding of it. So this might work, but, and in fact, what's lovely about this, and this is what's lovely about science, is you start with one puzzle, and once you start working on one puzzle, it's like the Andromeda strain. It becomes two puzzles, right? So now we have two puzzles. Why does nothing weigh so little? And by the way, you know, I don't want to forget about dark energy. And it could be that nothing weighs just the right amount and is the dark energy, or it could be that nothing weighs nothing, and if it does, we're going to call that Turner's theorem. And then what is the dark energy? Do you see the... So here's the most fun part. This is what gets theorists up in the morning, is when we have really, really big puzzles, like why the universe is accelerating, we know that the answer to the riddle will require a crazy new idea. In fact, we often, you know, when we're in the theory locker room talking to one another, we often say, yeah, you know, Jeff, that's really good. That idea is almost crazy enough to be correct. And, oh, but there's a footnote here. Not every crazy idea is a solution to a profound problem. Most of them are just crazy, so we have to sort them out. Let me run through a bunch of crazy ideas. So supersymmetry, we heard about that before. And if the world were supersymmetric, you can prove that nothing would weigh nothing. You could prove Turner's theorem. Even Brian Greene could do that. Our world is not supersymmetric. So the super partners don't weigh the same as their counterparts. So if supersymmetry is a symmetry, it's what we call a broken symmetry. Oh, this looks really, really good. So if we really were supersymmetric, we'd get 0, but we're not quite supersymmetric, so we get a small number. Oh, this sounds great. Unfortunately, when you try to see this mathematically, you don't really get a small number. You get the 10 to the 55 number. But maybe, you know, maybe there's a germ of an idea here. Here's another idea. I call this the most extravagant solution. And this is the cosmic landscape of superstring theory. So in superstring theory, there are many, many solutions, and they all have different energies, and the energies differ by an enormous number, a really big number, 10 to the 122 bigger than what we need. But you get all kinds of different energy states for the universe. And you get, in fact, you get 10 to the 150, sorry, 10 to the 500, 10 to the 150, 10 to the 500, same difference. And one of them will have the right value. Let's see, so let me try to understand the solution. Let me try to be a little bit of a critic. So we had this problem, and the solution is to invent 10 to the 500 other universes. And, okay, well, maybe it's right. And then this morning you heard about inflation. And maybe this is just mini inflation, because this kind of sounds like the same thing. Here's the picture that Alan Guth drew and Andre drew this morning. And so we just draw a miniature version of this. We're going through mini inflation. So if it happened once, it could happen another time. Oh, and then here's my son Joe. When he was 6, and that was a long time ago, I said, Joe, you want to get in on the fun. I was trying to make a talk. We used to have transparencies. I said, draw me a picture of dark energy. And this is what he drew. And, oh, he was so cute then. There he is. And you know what? I still think this is true. His theory has at least as much truth as any of the others do. Oh, and then here was my crazy idea. There is no dark energy. We've just discovered a new aspect of gravity, and I can explain it in one line. An empty universe accelerates. You might say, well, we don't live in an empty universe. Well, actually, we do. It's been expanding a very long time, and if you compare the density of the universe today to the times when Andre and Alan were talking about it, it's 100 orders of magnitude smaller. Unfortunately, this is poetry. What is it? You write, you know, you campaign in poetry and govern in prose. And so this was a really good poetry, but trying to put a theory to this, actually we do have a theory to this. Unfortunately, the theory did not explain the solar system as well. But that's a small detail. Okay. A big feature of dark energy is this pressure. And so we honored our former president, George W. Bush, with a parameter called W. And so that's pressure over energy density. And that tells you how the dark energy changes with time. And so if the pressure is equal to minus the energy density, so this is a plot, time goes this way and energy density goes that way, it doesn't change at all. If W differs from -1, then the dark energy can slowly increase or it can slowly decrease. And we'll come back to that. And what do we know about W? Well, we know a lot about W. Somebody's going to write his biography, but this is the W I want you to know about. What's remarkable is the measurements that we've made so far say that it's remarkably close to -1, kind of -1 to 10%. So it kind of looks like the duck, even though we don't want it to be the duck. So what do we know about it? Not much. It's smooth. It's very smooth. It's not particulate. That's really weird. So since the time of Democritus, you know, everything's made of particles. This is not made of particles. Because P is close to rho, it's very, very relativistic. It has repulsive gravity. It's the energy of nothing. So far, it quacks like lambda. But so the two big questions are, does it change with time? No, at the 10% level, but maybe if we look at it carefully. Do we have to go beyond general? Just because general relativity can explain it, that doesn't mean that it isn't pointing us to a new feature of gravity. And about a year ago, the Dark Energy Survey, a big experimental program to study the expansion of the universe, went underway. There are going to be big telescopes in space. I put the Large Hadron Collider here because maybe they'll discover supersymmetry. Oh, this is to end and to wake you up a little bit. From here to eternity. And I bet, how many people know who that guy is? Yeah, who is he? And what about the girl? Okay, good. So the producers this morning, we were looking through the slides. Who did he say it was? I forget. Bill Murray. No. Okay, so this is the slide your mom showed you. And they're droopy lines. Mothers are never wrong. And we also know that we're the middle one, the flat universe. So what's going on here? Well, as you were falling asleep, she said, darling, if there's dark energy, the story's a little different. And so that's the story with dark energy, is we know we're accelerating, not a droopy line. And until we know what the dark energy is, we don't know the future. Let me just quickly mention a couple of futures. If dark energy just stays constant, then we are destined for a cosmic darkout that pretty soon we'll only be able to see 100 galaxies. I go to Congress all the time saying, you know, in 100 billion years, we're not going to be able to study the skies anymore. We need to fund astronomy now. The argument hasn't worked yet, but what if the dark energy is increasing a little bit? So it's getting more and more important with time. Then in the future, there'll be a big rip. So the universe will get ripped apart. Galaxies will get ripped apart. Stars, atoms, us. Or it could be that dark energy is just one of those phases that, let me see if I have that slide. Oops. I'll come back to that in a minute. It just decays away. Or it could be that we recollapse. So all of the futures are open. Dark energy controls the destiny of the universe. So until we understand dark energy, we don't understand that. And here's kind of, to get you into the game here a little bit, this is energy density, this is time. So dark energy is pretty level. Matter just decreases with time. The density of matter decreases with time because the amount of matter stays the same and the universe is getting bigger. So if you just put these lines together, you see that in the beginning, dark matter was more important. Today, dark energy is more important. So the universe is controlled by these two dark titans. When dark matter was more important, that's when we made the structure of the universe. That's when things could cluster together. Now the universe is accelerating, and that crossover point was 5 billion years ago. And is that an important clue or a coincidence? And I don't know. So we're trying to figure this out. Maybe the most profound problem in all of science. You know, I thought I was the only one who shared this view, and then I looked at this interview, and in the interview, you betcha, Katie, I believe in dark energy. We can see it from Alaska. And I gotta, you know, this is, swear you to secrecy on this one. There is her 2016 bumper sticker. Okay, so what do we know? The expansion is, just because the expansion is speeding up. You can take that to the bank. That's a fact, just like dark matter is a fact. Caused by the repulsive gravity of dark matter, or maybe a breakdown in the theory of general relativity. While it quacks like lambda, lambda isn't good enough. And you know, the theorists, in case you hadn't figured this out, were clueless. We don't have a compelling idea as to what it is. This is a big, big mystery. The destiny question is connected to what dark energy is. This is a big, big mystery. And it's what gets me up in the morning. Oh, this is Alan Greenspan wanted a slide because he claims he predicted this. Because some of you will remember that he said brief episodes of inflation are, yeah. Okay, let me just finish with this slide, which is, I think, finishes the day. This is an amazing time in cosmology. It's an amazing time to be a cosmologist. Why? We know a lot, but we understand less. And so we're trying to put all the pieces together. You're seeing a work in progress. This is my daughter's artwork. I explained the universe to her. Really, really smart, went to Columbia University, and she was still smart after doing that. And I said, Rachel, what do we got here? And she says, Daddy, you have an elephant. And so do you remember the tale about the 6 blind men and the elephant? And that's the metaphor for cosmology, is we've identified all these pieces of the universe, these features of the universe, and we're trying to figure out what it all means and trying to put it all together, construct the big picture. Some of what we have is probably wrong. Some of the ideas need to be reshaped, but we've got these really big ideas, and I apologize for not giving full credit. We also have powerful instruments that are going to help us. We can't do this by pure thought. That's not how science works. So thank you very much for your attention.